Of course you can. All right. So we're just going to jump right into the swing of it. Now, mainly when I'm talking radicals, I'm talking explicitly square roots. All right. Those are going to be what you typically are going to be simplifying when you simplify quadratics. Now, why do you think we're dealing with solely square roots if we're talking about quadratics? What does a quadratic always have? It doesn't have a perfect square, but it does have it has a square. What undoes a square? Square root. So remember, when you solve equations, a lot of time it deals with inverse operations. So that's why square roots play a big role in solving quadratic equations. Okay? So just to kind of refresh your whistle, these are all perfect squares. So what's the square root of 25? 9? 100? 0? 1/4? 1/2? 64 ninths? 8/3? So with these guys, this is the same as square root of 1 over square root of 4. Same thing here, square root of 64 over square root of 9. Now, remember, it's generally agreed upon that positive real numbers have two square roots, a positive one and a negative one. All right, because remember, if you square a negative, it becomes positive. All right, so we designate which one we want either by including a negative sign or leaving it off. All right, so technically, if I took the square root of 4, what could the answer be? 2 or -2. So -2 squared is 4, +2 squared is 4. So we designated with a symbol called plus minus. So this symbol literally means plus or minus. So positive or negative 2. It's a shorthand. What about 36? 6 and -6. So plus or minus 6. What about 1/16? Plus or minus 1/4. Because, guys, again, is it not true that these equal exactly the same thing? Does 2 squared and -2 squared both equal the same thing? Yeah, they both equal 4. So that's what this means. It represents us writing both of those separately. Now, quick evaluation. All right, so if I'm trying to find f of 46 for this function, what do? Plug in 46 in for x. This will be 20 plus the square root of 46 plus 3. Now remember, any operation under the radical might as well be in parentheses. So you need to do that first. All right. So this will be 20 plus the square root of 49. Now, what do you think I would do next by PEMDAS? The square root, because the square root's technically an exponent. All right. So what's the square root of 49? So 20 plus 7, so 27. Now, that was just kind of a warm-up, just to kind of wet your whistle. Remember the old perfect squares. All right. Now, as honors, you guys need to at least memorize your perfect squares up till, I would say, about 16. All right. And also know the ones that end in 0. So like 20, 400, 30, 900. All right. So on and so forth. All right. So it would be like from 0 to 16. 0, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 215. No, not 215, 225, 256. All right. All right. Now, here's something interesting when it comes to square roots, which it deals with its multiplication. All right. So when it comes to square roots, all right, let's say we did letter A. What's the square root of 4? 2. What's the square root of 9? 3. 2 times 3 is 6. Then here, square root of 4 is 2. Square root of 25 is 5. 10. But now let's look at B and D. All right. 4 times 9 is what? 36. What's the square root of 36? 4 times 25 is what? 100. What's the square root of 100? 10. What's true? So if you look between A and B and C and D, what happened? Same answer, different way to write it. All right. So that leads into our next property. So you can rewrite multiplication of square roots. If you have the multiplication of two separate square roots, you can write it as the multiplication of those two numbers under the same radical. And vice versa. If you have two numbers being multiplied under one radical, you can separate it into two separate radicals. Now, this really comes in handy when we're multiplying two unfriendly square roots, and it'll give us a nice result. So in other words, we started out with non-perfect squares, but when we multiply them together, we get a perfect square. All right? So for example, letter A, I could rewrite square root of 2 times the square root of 8 as the square root of 2 times 8, which, what's 2 times 8? 16. So this would be the square root of 16, which is 4. And just for funsies, like let's say we put that in our calculator. All right. So let's say I put the square root of 2 times the square root of 8. And hopefully I get 4, which I do. All right. So that property does actually work. So I could rewrite this as a square root of 12 times 3. So square root of 36, which is 6. What about the last one? What do you think my answer would be without having to rewrite it? 10. How do you know? 20 times 5 is 100. Square root of 100 is 10. Good. Now, this reason we're talking about this property is it really comes in handy when we're simplifying perfect squares. All right? Well, simplifying non-perfect squares. Okay? So, simplifying square roots of non-perfect squares. All right? It's pretty almost completely irrelevant to algebra, but also becomes pretty standardized on tests. So it's a good skill to be fluent with. So in other words, a lot of times, especially like I'll say on the EOC, they don't want rounded answers. They want the simplest standard form or the simplest radical form. All right. So when we're simplifying square roots, first off, letter A. Let's just list perfect squares. So if we start with 1, what's my next perfect square after 1? 4, then 9, then 16, then 49, next 64, then And lastly, all right, so these are the perfect squares for 1 through 10. Now, reason we do this is because now look at letter B. So, square root of 18. First off, is 18 a perfect square? No, it's not. But which of these perfect squares could we use as a factor for 18? 9. So 9 is a factor of 18. So since 9 is a factor of 18, couldn't we rewrite the square root of 18 as the square root of 9 times what gives you 18? 2. All right. Now, why did I do that? Well, how could I rewrite that multiplication? Square root of 9 times the square root of 2. What's the square root of 9? 3. So in other words, simplified square root of 18 is equal to 3 square root 2. So 3 times the square root of 2. And that's essentially what you do when you simplify a radical. You're finding the perfect squares and you're taking them out. All right. So let's try a couple of these together. All right. So 8. All right. So whenever I do these factors, I like to just kind of list some factors because that kind of helps me. Now, 8's an easy one because what's the only factors of 8 besides 1 itself? 4 and 2. And is one of those a perfect square? Yep, the 4 is. So we can rewrite this as 4 times 2, which is the same thing as 4 times square root of 2. So what's the square root of 4? 2. And then we're left with the square root of 2 because we can't simplify that. So the square root of 8 simplifies down to the square root of square root of 8 simplifies down to 2 times the square root of 2. What about 45? 9 and 5 would work. So we got square root of 9 times 5. Square root of 9 times the square root of 5. So what's my answer? 3 times the square root of 5. Now, 48 might be one where you want to break it down a little bit. All right. So with 48, like I said, it helps to list factors. So what are some factors of 48? 4 and what? 12. All right. So this might not be the biggest one, but let's stick with 4 for a second. So let's say we did with 4 and 12. So we had square root of 4 times the square root of 12. I'm just going to go ahead and break it apart. So this is 2 times the square root of 12. Now, here's the question though. Could I break 12 down to have a perfect square factor? Yes. 12 then breaks down to what? 4 and 3. So leave the 2 out because that's still part of your answer. But now we're going to break down 12 to be the square root of 4 times the square root of 3. So this would now be 2 times 2 times the square root of 3. So what do you think my answer is? 4 what? Times the square root of 3. Multiply. So everything we're doing is multiplying. So guys, in other words, even though we didn't get the biggest square root at the beginning, as long as you get the square root and ask yourself, can I go smaller? It'll work. All right. So based off of our answer, what would have been the largest square root we could have pulled out? 16. So since we have a 4 right here, if we squared that, that would give us 16. So another factor we could have used was 16 and 3. But the reason I did this example like this is because it shows you that even if you don't get the largest perfect square, you can still work your way down. All right, let's do one more. Let's do F. So letter F. Now, take note, it's a little hard to tell, but take note of this negative on the outside. So since there's a negative on the outside, that means we're going to do what at the end? Put not on the inside. Put a negative, make sure that negative is still on the outside. So we're multiplying whatever we get by a negative. So 500. What are some factors of 500? A 5 and 100. That's pretty straightforward. So I have negative times square root of 100 times the square root of 5. What's the square root of 100? 10. So I get negative 10 because I got to include that negative times the square root of 5. Any questions on simplifying radicals? Now, this brings up a good point. What happens if, hypothetically, I had this? So if I had the square root of negative 500, we can't solve it yet. All right. So right now, as far as you guys know, no real solution because it's not a real number. Now, on Monday, we're going to talk about how you handle that. This introduces imaginary numbers. So yeah, there's real numbers and there's imaginary numbers. All right. So that's simplifying radicals. Now, the reason we're simplifying radicals, that leads us into a whole different type of numbers, which is irrational numbers. Now, you've probably heard of irrational numbers before. Off the top of your head, what is probably the most common irrational number you've ever heard? Pi. All right. What makes pi an irrational number? It keeps going and there's no consistent pattern. All right. That's exactly what an irrational number is. It has a decimal, but it goes on forever and ever with no clear pattern. All right. So pi is not the only irrational number out there. There are plenty of irrational numbers, and most of the time, those irrational numbers come from square roots or any type of radical, really. So, difference between rational and irrational. A rational number means that it can be written as a ratio of two integers. So, in other words, if I'm saying the ratio of two integers, what do I mean by that? What's another name for ratio? Fraction. So if I say the ratio of two integers, I mean that sucker can be written as a fraction. So some examples would be 3/4, -7/3, and 5/1. They either have terminating decimals, meaning they end, or repeating decimals. So for example, 1/3 is equal to 0.3, and it repeats over and over again. So it has a continuous stream of threes, but it's considered a rational number because it has a clear pattern. Irrational numbers is any number that's not rational. Duh. All right. So in other words, it cannot be written as a fraction typically. And there's non-terminating, non-repeating decimal representations. So again, the most common irrational number that you guys know of is pi. Another irrational number could be the square root of 2, square root of 3, so on and so forth. So in other words, any radical that is not a perfect square or a perfect cube or whatever is considered an irrational number. If you put in your calculator, so for example, let's say I put in the square root of 2. If I put in the square root of 2, I get some really weird decimal. And is there a clear pattern there? No. It's just a bunch of random numbers. Well, they're not random, but you get the gist. So, let's consider a number that is rational and a number that's irrational. All right, so let's look at 2/3 versus the square root of 1/2. Now, both of these numbers are going to be less than 1. So in other words, they'll be written as 0 point something, something, something. All right. So as a decimal, they'll be like 0 point whatever. So going back to kindergarten, if I drew a pictorial representation of 2/3, how many of these do I shade in? 2. All right. That's clearly 2/3. Now, off the top of y'all's head, you guys remember what 2/3 is as a decimal? 0.6 repeating. A lot of times it rounds off to 0.67, but it's technically 0.6 repeating. Now, let's write out all the decimal places that we get for the square root of 1/2. So I'm just going to put this in my calculator. So you guys don't have to, but I will. All right. Write out all those decimal places. So take a minute, write out all those decimal places. So that entire number that you see on that screen, write it out for letter C. So 0.7071067812. All right. You guys got it? Okay, now tell me. So it's 0.70 what? 7. All right. Now, why could we not draw like a picture representation of the square root of 1/2? So logically speaking, if you were given that number, what would I typically ask you to do? Round. So in other words, it would not be exact. We would have to round. All right, that's why. Now, could a computer do it? Yes. But as a human being, we could not do that and be perfectly exact. All right. Now, we're not going to do the whole thing for A, B, and C, but just note that these numbers, what do you notice about what's under the radical? What's true? They're not perfect squares. So all 3 of these numbers, what they have in common, they're not perfect squares. So that's exactly what happens here. All right. So if you don't have a perfect squares, non-perfect squares give you irrational numbers. Now, if it's a perfect square, that'll give you a nice, pretty number. Not a perfect square, it's going to look ugly. Now, let's say we had to kind of estimate. All right. So, if you're looking at the square root of 28, what two numbers, without using your calculator, would you think that square root of 28 lies underneath? So 5 and 6. Why do you think 5 and 6? So it is 5 and 6, but why? Right, because 28 is between 25 and 36. Because if we took the square root of these, that's what we would get. Square root of 28, 28 falls in between them. So that number would have to be between 5 and 6. So let's just put it in our calculator very quickly. So second square root 28. And is it in fact between 5 and 6? Yes. So write that down real quick because I'm going to have you guys repeat back to me. So that's letter B. So write down the entire number. All right, good. All right, what is it? 5.29. Keep going. 1. Okay, 1502. What? Thank you. Now, let's simplify the square root of 28. So that's where we're finding a perfect square. So if I list some factors of 28, what would be one that would contain a perfect square? And good. So we can rewrite square root of 28 as 4 times 7. So square root of 4 times the square root of 7, which would be what? 2 square root 7. Now, let's see if that gives us the same answer. So if I put 2 times the square root of 7, is that or is that not the exact same answer? Yeah. So we're not going to rewrite this, but it is the same as the square root of 28. All right. Now, last little thing and then we're done. So I know today's lesson is pretty dry, but it's pretty straightforward, don't you think? So sometimes adding rational and irrational numbers can give you either a rational number or an irrational number. So for these, we're just going to do a quick calculation on our calculator, and we're going to take a guess of whether it's going to be irrational or rational. All right. So let's do letter A first. So I'm just going to type it in, and I'm just going to let you guys tell me whether it's irrational or rational. So I have 1/2 plus, what is it? Square root of 2. So what do you guys think? Rational, irrational? Irrational. So that gave us an irrational. All right, let's look at the second one. So 4/3 plus square root of 10. I definitely did not put a plus. Second insert. All right, so just take a guess. Do you think it's going to be rational or irrational? So we're thinking irrational, and we will be right. All right. So without me even putting C in, what do you think it's going to be? Irrational, which it would be. So in other words, if we ever add a rational number to an irrational number, the result is always what? Irrational. Which that makes sense, guys. Let's say with the, if we did 1 plus the square root of 2, that'll just be 1 point and then whatever the rest of that is for the square root of 2. Okay, that makes sense. Now, let's do some classifying. So, square root of 25, is that going to be an irrational or rational number? Rational, because the square root of 25 is a perfect square. So this is actually a rational number. What about 3/7? Well, let's take a look. So 3/7, sevens are kind of one of those weird things. But 3 divided by 7, it's technically irrational, but because we can write it as a nice ratio, it's technically rational. So remember, fractions, regardless, even if they have like a weird decimal type thing, if they're a fraction and we can write it as a fraction, it's rational. All right, what about the last two? What do you think? Both of them are irrational. Actually, no. Look at number 2. What's true about number 2? Square root of 9 is 3. So is 2 rational or irrational? It's rational. So our irrational number would be 4. All right. Any questions on simplifying square roots or rational versus irrational? All right. So here's what we're going to do now. We're going to do an activity with this. So what I need you guys to do, I need one person from each group to grab 3 personal whiteboards and markers and erasers. Some taught it in 8th grade, some don't. It just depends on what teacher you have. Just grab them from here. So guys, if we're out of markers, you just grab them from the thingies as long as you put them back. So if you grab them from the cups, just make sure you put them back. Yeah, I do need it. Just put it back. All right, guys. So here's what we're gonna do. We're gonna play some simplifying square roots bingo. Now, I gave everyone their personal card, but I have a couple extras. So what I'm gonna do is I'm gonna give a group card as well. All right. So one of your cards can be a group card. So in other words, if your whole group gets a bingo on that card, you all win. All right. Now, here's how it works.